3, 2, 1, let's go. Welcome to another exciting video for the online section of Math 2070. Today we're talking linear independence, or at least our first run through of this particular very important topic. Alright, so let's set the stage for what this is all about. So let's remind ourselves, we were recently talking about homogeneous systems, so systems of linear equations where the right-hand side is identically 0, or in other words, I have the matrix equation AX equals 0, and as we noted, there are only two possibilities for this particular type of system. There's exactly one answer when x is equal to 0. Obviously, matrix A times the 0 vector must give us the 0 vector. Or there are infinitely many. So, one or the other, we're always in a situation where there are answers. So, that's good news. Alright, now, the goal for today, in this brief video, is to introduce a definition that's going to isolate the former behavior. So, the case when we have exactly one solution, because generally speaking, that's the world we want to live in, where there's precisely one answer that needs to be found. And in this case, the answer is really good. We know the answer is 0. Alright, so jump right in. Here's the definition. So we'll call a collection of vectors in Rn. Note M don't necessarily need to have the same amount. We'll talk a little bit more about that. These are linearly independent if I can find scalars with the property that scaling and adding these vectors up to the 0 vector forces my scalars to equal 0. So, in other words, the only way to create a trivial linear combination using my vectors is to use trivial scalars. So there's no way I can scale these using 5, 7, negative pi and get to 0. The only way it can be done is if I just zeroed everything out. So immediately we see that this is just a reformulation of asking that my homogeneous system has exactly one solution. Right? Recall that matrix multiplication, A times X, corresponds to this precise linear combo, where here we've got the columns of the matrix, and the scalars are the entry of the vector. Beautiful. Alright, so, note now, very similar to how systems behaved, where we can view them as just literally the equations, or we can view them as a vector equation, or we can view them as a matrix multiplication. Here we see now the situation of a homogeneous system having exactly one answer can be reformulated in terms of a vector equation behaving in a certain way. Nice. So with the definition established, probably a good time to talk about the ins, outs, and what have yous. So note, if you want to test for linear independence, mechanically it's super easy. We just create the matrix that has these as the columns and solve the homogeneous. If there's one answer, we're linearly independent. If there's infinitely many, we're linearly dependent, which is the word we use. So we don't say not linearly independent, we say linearly dependent. Alright, so let's point out that dependence typically happens more than independence. Because, it's actually the other way around. But dependence is actually easy to detect, because there's some very obvious scenarios where you can just immediately look at your vectors and don't have to do any work and go, well, these are dependent. So an obvious one is if I've got any vectors that repeat. So for example, if I have 1, 2, 3, 9, 4, 3, and 1, 2, 3 again, if I set up my augmented matrix for my homogeneous system and do some refing, because I've got these two identical columns here, when I ref, I'll have two identical columns. And note in particular, this situation, gave me a row of zeros. So here, I have precisely two pivot columns, but in order to get exactly one answer, I would have needed a third pivot, but as I noted, this column and that one are identical, so when we ref it, we are not going to pick up a 1 down here all of a sudden. Right, any row operation that turns this into 0 will turn this into 0. And likewise, and likewise. Alright, so no hope of ever getting another pivot column over here. All right. So, note free variable, homogeneous system has infinitely many solutions. There we go, we know these are dependent. Right now it works, again, as I noted, for any repeated vector, because when you set up the matrices and start doing the row operations, you're going to get a repeated column. And that's going to ensure that there's at least one free variable L floating around, and thus infinitely many answers. All right. So here we see our first sort of immediate sniff test for dependence. If I've got repeated vectors, party's over. Another one is if any of the vectors are 0, then done, automatically dependent. So for example, if I look at 1, 2, and 0, 0, similar situation. If I set up my augmented matrix and do my row ops, well, because I got a big old fat column of zeros, I've got a guaranteed free variable again. And thus my homogeneous system is going to have more than one answer. And as we know, independence is precisely the case when the homogeneous system has exactly one. Right. So, repeated vectors, 0 vector, immediate dependence. All right, and those are the quick ones. Those are the ones where you can kind of just do a quick little scan and go, all right, these are out. All right, now, what else? So let's build up from the ground up here, and let's start with a single vector. And note that a non-zero single vector is linearly independent. Now, this is a little weird to think about, because normally when we're talking about systems, you've got usually more than one variable, but right, it's possible you just have a system with one variable that would represent a single vector in your matrix. It's a weird thing to think of, but it's possible. And a single one has to be linearly independent, because if we formed our linear combination, well, I've got this scaled vector equaling 0. If this vector is non-zero, there is no way that this scalar itself is non-zero, because somewhere along the line I'd have a product of two non-zero things. I have no idea what just beeped. The cat's in here too. I thought he'd be yowling by now, but he's just messing around. Oh, yeah, there he is. Actually, maybe that's what was beeping. High quality content here. All right. Anyway, yeah. So if you have two non-zero things multiplying the other, you're getting a non-zero entry. So there you go. All right. Now, a pair of vectors being linearly dependent is pretty easy to see. And this is kind of an extension of what we just talked about, where if you have two repeated vectors, you're going to have dependence. Note that if they were scalar multiples of each other, you're still going to grab dependence, because if one is a scalar multiple of the other like that, then we can very obviously see a linear combo that will give me a 0 vector with non-zero scalars. Simply subtract this over or subtract that over. And then you've got a linear combo, and you've got it equal to 0. And this extends beyond just a pair of vectors. If you have a collection of vectors with two scalar multiple vectors, then linear dependence will happen. All right, so a single vector is only linearly independent if we're non-zero. A pair is easy to detect. If they're scalar multiples of each other, then party's over. 3 and beyond, it gets a little bit more subtle and requires some actual work. And basically, these are linearly independent if one of the vectors is a linear combination of the others. Very similar to what I was just talking about here, where you can simply subtract one of these over. Similar case. But this is the more subtle situation, because usually you can't visually suss out what's going on with 3 or more. With 1, it's easy. If it's 0, we're done. If 2, it's easy. If one's a scalar multiple of the other, your eye usually catches that. But for 3 and beyond, it's a little bit more not immediately obvious. So all of our immediate tests that we had here, I have non-zero vectors. None of these are obvious scalar multiples of each other. This is zeros here, so there's no scaling this one to create that one. I see a 2 that would scale. However, I have a 7 and a 9, so these are not scalar multiples. So how do we know if these are dependent or independent? Well, you gotta set up the augmented matrix and do the work in this case. There's no just sort of immediately visually detecting this just from the numbers. But here we see, when I do the row ups, big old fat row of zeros, I've got a free variable. And that tells us they're dependent, and in fact, it does you one better. it reveals to us that the linear combination that you seek is as follows. Here I have a -1 in the third column, so, and in the first row. Here I have a 2 in the third column, second row. Ah, beautiful. So this actually gives you a formula for what the linear combination needs to be, to tell us that our third vector is in fact -1 of our first vector plus 2 times our second vector. Good stuff. Neat little trick that in general works if you're trying to figure out which one is the linear combo of the other. Good stuff, as always. All right. Now, something that may have jumped out at you while we were talking about this, detecting linear independence. Oh god, Livy just showed up and made noises. I thought the cat was going to spoil this video and then it'd be my child. Alright, Livy, give me a second, okay?
Huh?
Go.
Daddy. I'm hungry.
Alright, go downstairs. I'll be right there.
Daddy? I didn't tell.
Alright, go. I'm almost done. Okay. Alright, so this is, yeah, we're doing good. Alright, so, to wrap things up for today, something you may have noticed, these matrices we've been working with so far gave us a nice square matrix. If we were in a rectangular situation, there's an obvious case where we automatically get dependence. So that's our final note for today. It's a very powerful tool. If we have a collection of vectors where the number of vectors is more than the Rn we're looking at, then you're automatically dependent. And that's easy to see sort of visually with this, because if I were to put a augmented matrix with these three, note I'd have 3 columns, which means I'd have 3 variables, but I would only have 2 rows, which means I only have 2 equations. So any row reduction that you do can only guarantee 2 pivot columns, but I always have more variables than pivot columns, so there are free variables, and thus there are infinitely many answers, and thus guaranteed dependence. Ooh, so here we see that in Rn, there is an upper bound on how many linearly independent things I can have, because once we get past 3 in R2, for example, we are always dependent. So if I have 3 vectors in R2, no matter what those 3 are, we're dependent. If I have 4 vectors, we're dependent. If I have 5. So we know that in R2, at most, you could have 2 linearly independent things. Ooh. Very powerful. I wonder if that's, like, super useful. Maybe it is. Alright. And that gives us our initial sampling of linear independence. We'll dig into it deeper as we go through the semester, and especially when we talk about vector spaces. Alright. That takes care of this topic. And next time we're gonna get even more linear. It's gonna be transformative even.